Okay, here's some notes on the symmetric slab. What we're going to do now is we're going to assume a slab waveguide with N1 greater than N2 and N2 equal to N3. Then I'll use WG as the abbreviation for waveguide. Okay, and what I'll do is first is I'll just go ahead and plot the refractive index as a function of the lateral position in the waveguide. Let's call that the y-axis, and I'll say that I'll label this distance here as the distance, the thickness of the slab. That's the thickness D, and our index will be N2 in the outside of the slab and N1 on the inside of the slab. So our plot will look like this. Okay, so that's the plot of the index profile of the symmetric slab. Okay. We're going to go ahead and label this as the so we're going to go ahead here, I'll draw the slab right underneath here, and 1 and 2 and 2 on the outside. I'm going to go ahead and label these. Inside the slab is called the core, and on the outside it's called the cladding. Okay, and it turns out that we can have both polarization modes inside this slab, and we didn't really go over in detail the reflectance equations in Chapter 2, but we do know that there are two possible polarization directions for a wave in a slab. Let me go ahead and draw my slab sort of in a three-dimensional way, like this. Okay, so this is just a section of that slab, and this will be our propagation direction. Okay, and I'll call that the z-axis. Okay, apparently this is the y-axis because that's the one transverse that slices through the slab. So here's the cladding, here's the core, and here's the cladding. So this is N2, N1, and N2. Okay? So we know that light is a transverse electromagnetic wave, and we can put light into this thing either with a polarization direction which is parallel to the slab, or we can put light in which is perpendicular to the slab. Okay, and let's see if I can get TE versus TM. What I'm drawing here is the electric field. We could draw the magnetic field, but it's perpendicular to the electric field. We usually characterize our polarization directions by the orientation of the electric field. And the polarization in which the electric field is parallel to the slab is called the, let's see, transverse. Transverse means, maybe I'll get it wrong here. I think this is the TM, the TE, called the transverse electric field polarization. And this is called the TM. And If the electric field is transverse to the core orientation, then the magnetic field is perpendicular to that, and it's the magnetic field which will be transverse. And so this is the transverse magnetic field polarization. Okay, so there's two different rays, two different possible polarizations. And they both have the same critical angle. Okay, so that simplifies our treatment here. And you can see that they both have the same critical angle. Perhaps I'll pull up a photo or a picture from the book from chapter 2 that shows that the critical angle is independent. I guess it's in chapter 3, isn't it? It's at the very end of chapter 3 that the critical angle for both TE and TM is the same. Well, this is the picture right here. So this shows in figure 3.23 of Peleus that both the S and the P waves, which are two different, just a different labeling of the TE and the TM, their reflectance goes to 1 at the critical angle. And both polarizations have a curve going to 1 at that same angle. Okay. So this is the basics of the symmetric slab, the definition of the cladding and the core, and the definition of the TE and TM waves in the slab. And I will start a new video for the next slide. Thanks.